Hi everyone, this is Lab 5 Faraday's Law. In this lab, the main goal was to become familiar with Faraday's Law, and the material we used were a magnet, a roll of aluminum foil, the magnetometer app, and a stopwatch. The physical principle we used were Faraday's Law that relates the magnetic field that changes in time to a curly electric field, the induced current, so the curly electric field provides an EMF that can drive current, the Biot-Savart law, which describes the magnetic field, Newton's second law, so the force is equal to the mass times the acceleration, and Newton's third law, for every action there is an equal and opposite reaction. In this lab, I let fall the magnet positioning the north pole downward into the aluminum foil and then measured the time it took to pass through the tube. Observing the magnet while falling into the tube, it changes its position. In fact, while it was inside the tube, it looked like it moved from a vertical position, so on axis, to a horizontal position off axis. We used aluminum and not another metal like steel because otherwise the metal will have exerted an electric force that will have attracted the magnet and so attaching it to the wall of the tube. Here are the values of time measured in the 5 trials. The average time was 0.472 seconds and the average velocity was 0.57922 meters per second. Here in the computational model, I first wrote down the constant and plot the graph of velocity versus time, and wrote down the measurement of the aluminum foil and the radius of it. Here the first part is to create the aluminum foil, and then I put the mu of the magnet, which I took from lab 3, which resulted to be 6.12. And then I wrote down the characteristic of the magnet. Here are the two functions that calculate the magnetic field and flux. Here is the simulation loop, where I calculate the time when it enters and when it goes out of the tube. And then I wrote down the gravitational force, and then calculate still the part of the magnitude of the force on the magnet. And then finally calculate the net force on the magnet and the bar velocity and bar position, and then plot everything. And here are the results. So the graph on the left show when mu is equal to 6.12, which is the value that I got from lab 3, and the time that was calculated was 2.657 seconds. While if I put the mu equal to 3.0, which is our theoretical value, the time that it took is 0.674 seconds, which is much closer to the average time that I got from my 5 trials. Here is a representation of the magnet falling to the tube, to the code. And here, what if the resistivity of the conductor were reduced as close as possible to 0? So the velocity should stop decreasing because the gravitational force should be equal to the magnetic force. And what if holes or slots were cut into the tube? In this case, it will still pass current through this tube in these slots, but the direction of the magnetic field they will create will be different from the direction of the magnetic field we observed in our experiment. Finally, the bar magnet creates an induced current on the aluminum foil, which creates a magnetic field that is opposed to the magnetic field of the magnet, making it change position during the fall and also slowing its fall. The value of mu makes a great difference. In fact, with a value of 6.12, the time calculated by the code was 2.657 seconds, while with the theoretical value of mu 3.0, the time calculated is 0.674, which is much closer to the average time obtained from the 5 trials.